everybody, from your favorite artist electronist here, Mr. Q12. I finished this contraption, this ESR meter. ESR, it stands for equivalent series resistor, specifically for electrolytic capacitors. This specific instrument is powered at 8 volts, specifically at 8 volts. You can see here on my diagram. I actually changed the diagram correctly this time to reflect that I used the potentiometer. Last time I made the movie, it was two resistors. You can barely see them there, that one and another one there where I put this potentiometer. But this is how it's looking right now, and you can see the potentiometer there. It is not powered right now, is in off state, is absolutely no power, like you are seeing here. All right, let me open my VirtualBox. So I'm using this VirtualBox, this Windows 7 inside this VirtualBox to run this program 3ds Max 7 that is not working in Windows 11. That's why it's working only in Windows 7. Actually, I have Total Commander here. And this is my save file for this project, for this model, for this 3D model that I concepted it here in 3ds Max. Let me start with the beginning, which was this one. So like this. This was the 3D model of the case, various ways of designing it. This is the first version. This is the second version. I thought about how to fit everything together, how to earn the design, how it's looking. Then this with a little bit of oblique back. And then I was thinking to use this model here, this case model with the measuring pads while balancing. But quickly I realized if I'm pressing on those pads while I'm measuring something, everything will move back and forth. So it is not a good idea at all. And finally, I got to this model here. Looks right. As you can see, I'm using this green cylinder inside it, and then I modeled from reality this milliamp meter. I actually measured it and I modeled it in another save file, and then I imported it here. And here, this one is the actual final version with the meter inside it, with its real dimensions. It's scaled up, everything is scaled up. These are a bit more bigger because I didn't care about the dimensions, only the design, how it looks and how it feels. This is actually moving, exactly like in reality. Yeah, see? Up and down. I made a small mistake here. I put these screws. I didn't see it, but the screws are on top here, not down there. I also planned to put an LED here. This is the power LED that is announcing me that the device is powered. And I didn't implement it in reality. It is looking a bit more sexy here in 3D. It's a bit more nicer than in reality. Like these two blue ears outside, that one and this one. It's a bit more, aesthetically pleasing. I like it more here in 3D, but in reality, it's close enough. I also modeled exactly how I wanted this curvature you are seeing of the case, external case, how it should be. Yeah, you see the light reflecting it is actually showing the contour of the shape. As you can see here in the back, I was thinking on using metal sheet formed braces that I will glue or screw inside this round panel there, but I didn't use those. I used plastic ones. Because in reality, I had a very small tolerance here, and here in 3D, I didn't realize how small tolerance it is in reality. Another point is that if I had a 3D printer, this model that you are seeing here in 3D was a bit more interesting in reality than it is right now with wood, cardboard, and some melted plastic here and there. But I do not have this kind of technology, so I did what I had to do to make it work and feel as I originally planned here. And yeah, it's good enough. It's good enough. This is it. I hope you like it. And if you like it, leave a like there. And also a comment. Alright, so this movie is a presentation about how I made my new device, my new ESR meter. And I will show you some pictures right now from the stages of building this entire contraption, this entire device. This is the updated, the latest version of the circuit. It is as I'm having it right now on my table. Here is in the very, very beginning when I was making the board. Here is the paper. I thought how to place the components. And here is the actual cardboard at the dimension I wanted it to be, populated with the real components and the real circuit cardboard, this one here. And these are a couple of scraps, pieces of metal sheet that I'm using for this as pads for the components to be soldered onto. And apparently I don't have a picture with it finished. I was concentrated on showing the process of making the case, which it took me a ton of time and it was not nice to do it. Here I'm using matchsticks. You can clearly see these are Romanian matchsticks that I took a piece of cardboard, I bended it, and I hold it in place with this clamp. And then I literally glue with this shoe glues, glue for shoes. You can see here a shoe and a foot of a man, cartoony. It's my favorite glue that I'm using all the time and is cementing and is behaving very well in general. And I'm gluing these matchsticks on this cardboard. Another view with my box of sticks. There is my finished circuit already encased in its cover box there And here I finished to glue all these matchsticks up to this level here, and that's it, not further down. And I'm starting to filling with melted plastic. You can see them here, HDPE plastic type. Here is another angle. This is the shape of this cardboard that you are seeing, but is on paper here. This is the paper test to see if it's long enough and the shape is good enough around this meter element. You can see it here again. And also another angle, and also my HDPE box of, I cut it by hand, everything that you are seeing there. And also here is my electronic board that I didn't make a picture of it. And here is when I was filling with plastic between the gaps there. This is a look from the front. And here another evolution. I'm putting some white plastic and another angle. And here is the orange plastic in the back, also on this other side as well. And I think this is very close to the final version. And I filled everything here not to see the matchsticks inside. And here this is the next step when I cut this piece of wood. But actually this is not wood, it's a very extremely thick cardboard. It's from a very long time ago, very old. It's very fragile. It's not like a piece of wood. It's very easy to damage it, and it's not a good material actually, but it's good enough in this case. Another angle again. And here I put the top cover, the top cardboard. I glue it on top of everything. This very thick cardboard, let's say it's wood, but it's not wood. And the matchsticks, I glue it on top of everything, even the plastic probably, with the same glue. And another angle from the top. Look how clean and beautiful it's looking. And the back is looking like shit, but who cares? These are testing wires. I leave them there for further tests. I didn't took them out. And here I'm still clamping this external sheet of cardboard. And this is how I catch to stay on position this clamp with this vise. Another shot. These are more like a beauty shot from the construction of it. And I made this plastic ears, this orange one and this other one, to catch this meter inside it. Another angle. And here is the latest picture, probably today I took it, when I made this label from a normal paper, a colored paper that I purchased a long time ago. And I already measured and marked everything. Here I measured everything and it was linked. You can see the wire that is going inside, and I'm actually testing there to see exactly where those bits are. Oh, here it is, the circuit board outside, and this is the LED, the latest attachment. I use this resistor, this funky resistor here, on positive rail, and this is actually the negative rail. Here you can see the negative rail there, and I bend it that way to get outside. And I put this 820 ohms I used for that resistor. And this is a beauty shot. This is finished, the finished product, the finished device. And here is a close-up and another shot here, and that's it. Now I will power it on. It's exactly 8 volts, 20 milliamps. And voila, this is an LED here on a wire. It's very adjustable, the distance and the angle of it. Actually, this is not a short. This is counting as 0 ohms, because this is measuring the resistance. And when I'm shorting here, it is actually measuring the resistance. And right now it is calibrated to show exactly 0 ohms or 0 resistance. This is my test if it's working correctly. And it is landing, as you can see, on that other red line. And it says there it is in air with this gap here is having the no resistance value pretty much. Let me close it a little bit. And as you can see, I made a new label. Here is a piece of paper that I glue it with 3 spots of glue, but very tiny here, there, and one on top there. And I literally glue it on top of what it was before, the milliamp meter. This is exactly the same meter. It was measuring from 0 to 1 milliamps. These are small value milliamp meters. Unfortunately, I couldn't make the circuit go to the entire scale from this corner to that corner. It's a little bit narrow from 0.2 to 0.8. I'm good, but not that good. Making abstraction of this narrow range, it's working fine. So this is how it's looking right now. I look on my previous movie when I made the test there on the breadboard. This is the old circuit that I used last time, and this is the schematic of it. That's the potentiometer there that I updated here in the circuit diagram. Let me show you some measurements. Like I said, this little light, it's a LED that I put a wire, and less than 1 kilo, 820 or something ohms, and voila, is 1 kilo there. It's because I wanted a very bright light. Let me show you the model of the LED that I used. Is this one here. This is the type I used, and they are a bit unusual from the way I'm working with LEDs, but I know they are very bright, a bit more brighter than the 1206. Is my impression, of course, my subjective impression. Actually, how I made this resistive scale, ohms scale there, I took a bunch of this kind of resistors that are 1% tolerance, not 5%. The entire scale, I measured it with only this 1% tolerance. And this is, like the label is saying there, is 1 ohm. There are a bunch of shadows here, but it's landing exactly on 1 ohm. And let's try 10 ohms. I will not show you every value there, but believe me, on my word, I did used a bunch of resistors, different values for every single one of them. Everything is measured. And this is my 10 ohm resistor. And it's right on the money there, as you can see. 100 ohm, right on this marker. It should move a little bit, and it does. At 100 ohms, here it is, 100 ohms, and it's moving a tiny little bit. Curious enough, as you can see, here is another marking.
1 kilo, it says there. And for some reason is able to measure 1 kilo ohm. This is a 5% tolerance, and you can see the deflection is going there, is going outside the air gap. Most probably is the circuit, yeah, you see, it's moving a little bit outside. It shouldn't, but for some reason, then I tried with 10 kilo and it doesn't move at all at 10 kilo. I was thinking maybe it's moving more to the right, but it doesn't. Pretty much this is the test I wanted to show you that is working. Let me show you the capacitor reading right now. Again, this meter, what I'm having here, is used specifically for electrolytic capacitors. In this case, less than 8 volts capacitors. It's a bit limited from this point of view, a voltage of the capacitors that you can check. For my needs, I like it. So I have to respect the polarity I marked here. Actually, you can see it is a electrolytic capacitor symbol there. And if I'm checking this, it's showing 10 ohms, a little bit over 10 ohms. So this might be, this capacitor is 1 microfarad at 50 volts, and probably because it's so much voltage difference, maybe it is another scale, I don't know. I should test this capacitor at higher voltage, at 50 volts like it is rated, not 8 volts like it is right now, or even less than 8 volts. I'm not sure exactly what voltage I'm having here on the testing capacitor here, because this left side is an oscillator and it's creating an alternating current, like a sinusoid probably. I didn't check it, I didn't measure it. So it might be even less than 8 volts is what I'm saying. But I have other capacitors here that are checking correctly. For example, this 25 volts capacitor, 220 microfarads, it says there. And I will respect the polarity here. And this is going less than 1 ohm, like 500 milliohms. I think is good enough. I think it's very good. Also 25 volts, 22 microfarads, it says here. 1 ohm, a little bit over, 1.2 ohms. This is a very small one. It's scrapped from somewhere. I have no idea what voltage it is. It says there 35F and 10, probably 10 volts. Who knows? And I think that is a minus on these ones, not a plus. Let's see. I never test this. Yeah, good enough. 1-ish. And this is a tantalum capacitor. I have no idea what value is this. 107 it says there, but and a strange number. I will short it like this on a piece of metal, or like this. And I think that marker is on positive, this tantalum ones. So I have to put it like this. Is it working? Oh, perfect. Almost zero. Almost zero. Very close to zero. Super, super. And this is a very small capacitor. This is just SMD capacitor. I hope the gap is good enough, what I'm having there. This is my plastic tweezer to actually manipulate it there, not to influence anything. Oh, super. 1 ohm, 1.5, 1.4 ohms. Fantastic. Super. Super. And I like it. I like it. So this is what is doing this meter for my needs. Usually I'm not working with high voltages. Rarely I'm working with high voltages. Usually I'm using 5 volts circuits, logical circuits, circuits with microcontrollers most of the time, the majority of time. So the capacitors I'm using are this kind of very low voltage. And this meter will more than suffice. It will be more than sufficient to check if something is fucked up. I have this kind of model as well, also again scrapped from somewhere. Let me short it. And I have no idea which. I think this is a minus here. Minus. What the hell? I have no idea which is minus. Oh, it's having a bump here. Maybe this bump is suggesting that is the fuck. I have no idea. Okay, it's not very clearly marked. Yeah, 10 ohm. 10 ohms. And this is the value of it. It's 10 volts. Check this out. 10 volts, 47 microfarads. So, was that sure? This is a fucked up capacitor. Let me turn it around. Yeah. Again, these are scrapped components from some boards recently. But what I'm showing you here are different categories, different types of capacitors that you can check with this instrument. Yeah, maybe this one. 10 volts, 220 micro. And this band might be negative, this band. I think this gap is positive here, sometimes. Oh yeah, almost 2 ohms. 1 point something. 1.5, 1.6 ohms. Equivalent series resistance. 10 volts or V6, 6 volts, maybe, who knows. I don't care. Different types of capacitors is what I wanted to show you. And now let's go to the way I build it. And it was a struggle. So it was a struggle to make it as you are seeing it. I watched the last movie when I made the testing circuit here. It passed from then. So last month on 28. So exactly 1 month. It took me to build all this case. Not the circuit. The circuit it took me like 1 day to make it. This board. but the entire shebang that you are seeing here, also the 3D modeling, I had to model all this thing in 3D to make an idea how I want it to look cool and to look a little bit retro and to look a little bit interesting to use. I really liked the idea to pivot this entire analog meter, but I made a couple of versions until I reached this final stage that you are seeing here. I will take everything out just to show you how it's made. This is how it's looking from behind with this tiny plug here that also I scrap it from somewhere and I repurpose it, and I also labeled clearly. It does show here a plus. I'm not sure how well you can see it, but it is a plus and a minus here, but it is stupid. It's too close to this thing. I remark it, and here I made myself a reminder that it needs exactly 8 volts from the power supply unit, because I'm stupid and I'm not using it every day, and in time I will forget what is what, and that's why I'm specifying exactly what type of voltage I need, how to power it, not to burn it out. All right, let me disassemble it and show you some bits of it. So I'll start by taking out this very nice plug. You have to squeeze this too and then drag it out like that. Very nice, I really like it, and I have it for some time. Unfortunately, the wires are not really correctly colored. It's black and white, but it's good enough. It took me a ton of time to build it and a lot of head scratching. It's not perfect. It's having some errors of alignment. It's a little bit like wonky, a tiny little bit if you are super paying attention to the thing. This LED that you are seeing here, this is a core wire that I can bend it on shape, on whatever shape I need. So I really liked the idea that is moving like this, depending on where I'm placing it on my table, if it's far away or closer to me, like right now when I'm filming from top down, I can do this also, and I can move it accordingly. So I have these 2 screws here. Like I said, I had a ton of head scratching how to make it, and it was not fun. It took me a ton of time to actually finish it, and I made 1 part per day, and a lot of days that I didn't do anything. I was working very, very slowly, extremely slowly, because I didn't have the energy for it to concentrate on it. I had a lot of troubles lately to deal with. I moved a lot of stuff from my home here to my other home. All right, so like I said, so this is the circuit board. This is a piece of metal sheet that I actually took it from diskette drivers. I had some around that I took them from a scrapyard, and I repurposed this sheet of metal from that. Is extremely malleable, extremely bendable, very easy to bend. This is very thin sheet, and I glue it to this. I didn't use any kind of screws. This bendable wire, solid core wire, is the last thing I added to this. In fact, this night, right before I start filming, I added it because in original design I had a power LED, and also on my circuit diagram I have a power LED there. Here actually it's mentioning their power LED, and this is the power LED to also announce me that the circuit is receiving power, and also to illuminate the display, so it's having a double function here. To take out the circuit board from there, it's a bit funky wonky like that. I have to use a tweezer here because this is cardboard after all, and it can break if it's stressed, and already I stress it a bit too much. It's actually bent inside like a normal box. It's actually very easy to take it out, but a bit more harder to put it inside. And I didn't plan to disassemble it fully, but I will do it this time. Only this time. After this movie, it will remain closed most of the time. And this is the sense how this is coming out. I also have a paper with the diagram here. I will show it in a second. And like that. And I will not take it out completely. I will only show it like this. The power wires. This is the positive, negative power wire. And this is how it's connected. This wire, this plug to the meter is catched here and there. You can see it here as well, the original drawing before I made this cardboard. So this was the original layout, and I duplicated on the cardboard there from here. This is the original idea, how to place all the components. That's why I keep it. And on the back, I duplicated this circuit here, this diagram. I duplicated it. It's the same thing, including the pot here. And I kind of I got out of space here a little bit. It is reasonable, okay right now. Also some details there that are most important. And I'm keeping this inside, and it's readily available. I also will keep this original diagram in my book of circuits as well, so I will have this too available. But if this will disappear, this will remain inside the device. This LED is using this 800, very weird markings here on this resistor, very retarded markings on the positive rail, and this is negative rail that is coming from there somewhere for this potentiometer. If you remember, on my last movie, I mentioned this is to negative rail and this is for positive rail, and that's what I'm having here as well. This is potentiometer is 2 kilo, 202 potentiometer. This is the diode, this D1, I think, that one. This is 22 nanofarads, the same as this one. 1 nanofarad here, 100 nanofarads. This is the 555 chip. This capacitor here is also a scrapped capacitor, this one, and is this one here in the circuit. Is this 100 micro and 100 nano, I think, probably this one on the 100 nano on the pins of the chip. This is how it's supposed to be actually on the pins of the chip. That's the negative rail for the 555 chip, and I linked this wire for the meter to the negative rail because this meter is on the negative rail there. And here is through that 3.6 kilo, and here this is the 3.6 kilo here is mentioned there, LR2 3.6 kilo to the meter positive, this pad. I actually mark it there. And pretty much that's it. This is the entire circuit diagram, how it's looking, and I hope you like it. All right, if you like it, do make a comment about it, and let me re-ensemble it back, and you will see how fun and easy it is to re-ensemble it. It's not hard, but it's not fun. It was a little bit more easy than the last time. Probably repetition is the mother of learning things, and that's it. Voila. And another detail, interesting detail, if I have problem, I actually had a little problem with the needle to center it where I needed it. If I can drag this a little bit out like this, and this is the potentiometer here, very strategically placed here in the margin, that I can move it a little bit and recenter to fit exactly those red markers that I have on my display. By the way, this is also cardboard. You are seeing two ears here, this ear and this ear. I glue it to the box. The box is glued to this sheet of paper, and this is paper, and then I screw it. I didn't want, so you can see it's flapping like that, and it's hold it only on these two screws. And but it's good enough. It's not moving left and right at all, only up and down, and not forward and backward. So it's okay, stable. It's stable enough. It's good enough. And these are very thick wires for the power, also stable wires, not flimsy to break easily. All right, so that's the electronic part. Now back to the mechanical part. This is plastic, melted plastic, that I melted it with my iron. Right now is powered off, so I melted it with my hot iron. And this plastic that I use is this type of plastic, HDPE. And I inserted a screw there, and I calculated everything, and it was hell to fit everything. I actually have this silicone rubber inside the hole there, and the same is here, to make it move and remain on the position. So this was an afterthought, and I don't have to take it out from here actually. I can take it out from here. And voila. Ta-da. So this is the module, the meter is exactly like this one. I had to clean, to cut. As you can see, the brand new is having all 4 holes and ears, but this one I had to modify it to fit my design here, so I cut off top ears. And here I melted this HDPE plastic to actually fit exactly, especially here in interior, to fit the roundness of this model of this meter here. And I encastrated a nut here, is metric 4 screws and nut. And yeah, it took me 1 day to make one and another day to make another, because again I didn't have the energy and the dedication to stay and work non-stop. Then I had a very big problem how I'm catching this to this element here, and I used this screw, which was a bit, this was the hardest part, how I'm catching this to this. I didn't want it to glue this. I wanted it to reposition it, is the best word, you know. If I needed a little bit of tolerance, if it was stick there, if I was gluing here, I didn't have a way to reposition the thing. And it's good to have tolerances and a little bit of play, usually, not to make it super fix, because mistakes are made, you know. And this is wood here, piece of wood that is only through here, this part here. And this is not filled with plastic, but matchsticks, like that. And you cannot see it. Here I didn't bother to finish it up like I did finished it here in the front. I don't particularly like this color here, but now it is what it is. So let me re-ensemble it back, and I hope I didn't screw it up. Oh, I also modified another mention. I did mention before. Yeah, you see that component with like 2 sheet of metal right now is on the center and is making contact with this pivoting knob here. And instead to move the needle way to the left there, I moved, you see it's a yellow wire there catched on that solder blob. So that is a thing that I could move it with that blob and that yellow wire. So I move it is a piece of sheet metal that you can move it left and right, and it will deflect the needle as well. So that's another modification that I did, because I observed, you see this yellow wire here, and that blob of solder, it's moved. That one is moved, and the two sheet metals are centered on this pivoting knob. So I made it like original, like it should have been in the beginning. And pretty much I took a piece of paper, and like I said before, I glue it here, and I measured everything, and I made the markings with the measuring. And this is a close-up, if you want, of it. Yeah, it's looking very nice. I like it. Because as you can see, the writing is right on the top part of the label. And this, as you can see, this original one is having this circle, this plastic circle, white circle, and is a little bit covering, a tiny little bit is covering, and you cannot read it correctly. So I took this one off from the original. You see, the original is more elegant with this circle, but now it's more functional. You can actually see those numbers that I originally placed them too much on the margins. So that was a little bit of extra modification. I didn't thought of it originally. So yeah, from now on, it will not be disassembled again in its life. I wanted to show you the work I put in it and how weird it's looking underneath the hood internally. And as weird as it looks, it is doing the job as I intended, as I envisioned, as I wanted it. This is the silicone rubber here. All right, it remained there. And I'm pressing in force this one here, pretty much. And this is it. And this is helping to maintain the angle. It's not super, so as you can see, it's very flimsy and fucked up, but when it's completely assembled, it's good enough. Yeah, it's relatively easy to assemble and disassemble it. All right. I'm strengthening it by hand. And let's see if it's working back again, as it should be, like this. Click. Very, very interesting way of catching it. Unfortunately, I don't have that many. This is the only one that I have, and it's interesting. It's interesting. I like it. I'm pulling it up, and it's alive. And actually, this is a good test when I'm doing this to check. Come on. When I'm doing this, is a good test to check the maximum and the minimum here. You know. And if I don't like it, I can adjust it from that potentiometer a little tiny little bit left to right. Yeah, it's perfect. From my angle, from how I'm viewing it, it's perfect. And this is it. This is the construction of it. I disassemble it. I show it to you with all the details. I was thinking this little device, it is actually very good at measuring very low resistance, at least up to 10 ohms. You can measure everything else that is resistive, like a piece of nichrome wire, probably, that you need, you know, for very weird resistive loads, resistive elements, resistive. If something is burned inside, it will create a little bit of a resistive black coating sometimes, and you can check it with this instrument. So it's not dedicated absolutely to measuring ESR equivalent series resistors for capacitors, but it can be used for other things as well. Is my opinion, of course, but mainly I will use it only for measuring capacitors for my needs without buying anything. This is literally for free. It took me a ton of time to build it, but I'm very, very, very pleased with the Chiquit and with the final product that I'm having here, and it's for free. It's for free, even if it took me like 1 month and another probably a couple of days for the original test on the breadboard here. Yeah, it took me some good amount of time to make it in reality. But another very important thing is that I don't have a 3D printed. I had to play with this kind of materials that I have: wood, cardboard, melting plastic with my solder iron. It does the job, but it's extremely slow to work like this. It should be interesting if I will put my hand on an actual 3D printer, but those are super expensive, especially for me, a guy from Romania. I don't have that kind of money. I always was poor, and I still am, and I have the poor mentality. I don't think I will ever get a 3D printer, but I'm thinking to build one, maybe. I'm not sure. I'm contemplating the idea. Probably there are some quick and dirty ways of make a very basic 3D printer that will do the job. I'm not completely sure right now at this point in my life if I will go to such a complicated, because I'm very aware how complicated it is to build such a machine. It must be very, very precise to work correctly and not to fuck it up. This is it. Thank you very much for watching. Thank you very much for understanding and appreciating, and please leave a like and also a comment. Why not? Try to praise me, try to praise my hard work that I did here, because it was super hard to make it. And that's it. I leave you with this, and thank you very much for watching, and see you next time on my next project. Bye bye. From your favorite artist electronist, Mr. Q12. Bye bye.